Okay, so now I'd like to introduce today's Limnoseries presenter, Mariana Meerhoff. Mariana is a full professor in the Department of Ecology and Environmental Management at CURE Universidad de la República Uruguay, and she's also an honorary associate researcher at the Department of Ecoscience of Aarhus University in Denmark. Her research focuses on global change impacts on freshwater systems, particularly climate warming and land use changes. She's published more than 115 peer-reviewed papers and several book chapters, and her work has been recognized with several national and international awards that you can see listed here. Her talk today will cover some of the different global change impacts on freshwater ecosystems and some of the approaches used to study those impacts, feedback mechanisms, and potential resilience mechanisms. So now I'll hand it over to Mariana for her presentation, and after we will have some time for questions from the audience. So thank you all for joining today. And Mariana, now you can take over and share your slides. Thank you.
Yes. Thank you for the invitation. Yes. Hope this will work fine after all the problems we had at the beginning. Of course. Of course, there's always some details. And yes, can you see my screen in presentation mode? I'm fine?
Yes, it looks great.
Okay, excellent. Okay, thank you again for this invitation. And I would like to say that the GSA Limnoseries are fantastic and they're very much aligned with also the initiative that from SIL, which I'm the vice director in the education committee, we are trying to do similar things. So it's fantastic to see all this different initiatives to get us as a whole international community studying and understanding freshwaters. So this conversation today would be on how to address both global change impacts and the resilience of freshwaters. And well, we wouldn't need to remind us, but we do need to remind the rest of the society that freshwaters, particularly small ones like ponds, shallow lakes, wetlands, and the headwater creeks and streams, make a disproportionate contribution to biodiversity and to many other ecosystem services and contributions to society. Yet, small water bodies are among the most vulnerable and the least protected ecosystems across the world. So in very few places there is actually protection and even monitoring programs that address these so valuable type of ecosystems. And this is crucial because in the length of a human life, that is since the 1950s, human activities have become the major force of transformation of the planet. Here in the figure, we see the planetary boundaries images, and we see that for 7 out of 9 major dimensions of the key for the functioning of life as we know it have been passed, have been crossed. And we are moving away from the safe operating space for life and for human well-being. And many of these dimensions that have been passed are affecting freshwaters. And among these is the use, exploitation, and pollution of freshwater, changes in the hydrological cycle, changes in the fluxes of nutrients, major phosphorus and nitrogen, and land use changes, biodiversity loss, and climate change, all acting and affecting the state and the functioning of our lakes, streams, lagoons, and the coastal areas. So how does global change impact freshwater systems. What do we know in a nutshell, or I will show briefly some major trends that we see today. So first of all, we're seeing in the past 2 to 3 decades, we're seeing a major decline in the capacity of storing fresh water in both natural and artificial lakes. So lakes and big reservoirs are losing their capacity to store water. And this is because water is changing where it is. So there's a lot more water that is now in the atmosphere as gas than it's liquid on our surface ecosystems. So this is despite the melting of glaciers. So we are really losing a lot of the liquid phase of water in our reservoirs and big lakes. And this is happening as a trend all over the world. And you can see places where this change is very, very dramatic. Also, we're seeing a widespread increase in the salinity of water. And this, again, is very, very serious. Many places of the world, despite in some areas, there has been a freshening of water, and that's associated with melting of ice. But these two, so we have less water and more saline water. And also, water quality is deteriorating. And in this image now, we see the changes in mean temperature that is perfect for the expansion of blooms of microcystis. So what we are seeing here is the poleward expansion of microcystin hotspots. So in the changes in color, you see from historical values, present values, mid-century, and the predicted for late century. So we see this expansion into climate niche of microcystin, and therefore more increased risk of having toxic waters. And we are also seeing deoxygenation in lakes and rivers that is increasing at a quite dramatic speed. So the images are really serious. So we see that these global trends are very rapid, and that are key elements of the functioning of our freshwaters. So these are global trends. And why are these? Why are we seeing this? So we know that there are several stressors that are affecting all sorts of waters, as we see in this image here. So still fresh water like lakes, lagoons, and ponds, running fresh water, and also marine areas. So all aquatic systems are stressed by what are now called grand ecological challenges, because they are so huge and difficult to address. And very often they interact. So ecosystems are exposed to all these stressors very often at the same time and at the same place. And some of these stressors are affected by climate change and also land use change and pollution. And some of these changes are biological. So they create a kind of cocktail of stressors acting together simultaneously on many of our ecosystems. And if we have to classify these dimensions of climate change into specific changes, when we want to analyze the impacts, what are the effects of all these patterns, these global processes, so we can dissect them and classify it into physical, chemical, and biological stressors. Each of these groups cover quite a range of processes. So from habitat alteration, we can be talking about the advance of urbanization, fragmenting habitats or disappearing habitats, damming of rivers and streams, and advance of other productive uses of the land like agriculture and so on and so forth, light pollution, changes in hydrology, temperature, of course, with climate warming, and then all the chemical parts of global change that are a massive amount of emergent contaminants, new contaminants or substances, pharmaceutical, drugs of abuse, cyanotoxins that are natural, super potent toxins, changes in salinity, as I mentioned before, hypoxia, anoxia, acidity, CO2 because of climate change. So all these changes are happening together. And we see in the literature that it used to be a few decades ago that the chemical stressors were the most studied, and all with the different kinds of biocides and fertilizers and industrial products. There was a lot of studies in the 80s and 90s, and then literature has been changing to incorporate more focus on other dimensions. And of course, there are new things happening like microplastics and nanoparticles. So there are new trends now rising in the literature again about the chemical pollution. And then, of course, we have the classic biological changes, so changes in biodiversity for various reasons, overexploitation, loss of habitat, diseases, and the eruption in many places of non-native and invasive species as well. So these stressors are so many and often interacting that it's often difficult to analyze them, right? And to try and understand the effects of such impacts. There are different approaches that vary in their determination of mechanisms, in their replication capacity, in how realistic they are. And each of these methods have advantages and disadvantages, but they cover from theoretical models, mathematical models, or mechanistic-based models to remote sensing works that are increasingly becoming more and more seen in the literature with the advances in teledetection and satellite imagery, paleo studies, long-term series or monitoring studies, which are crucial for basic design, so before after control impact design, when we want to understand the effects of a particular disturbance that happens in a pulse way, for example. Then we have space for time substitution that are particularly used for climate change impacts analysis, and experiments. Experiments allow for multi-stressors studies, and they allow for mechanism detection, despite they can be a bit unrealistic compared to other of the approaches. And then how do we know or how we try to gather all this information together when there are so many studies and they have different results quite often? So one of the denominators, or what is considered to see or to say what can be expected with climate change, is if there is coherence among these different approaches. So if several of these contrasting methods say the same, then we can be more confident on, okay, this is what we can actually expect with this particular stressor or with this dimension of global change. So we have to seek for coherence when we aim to make stronger predictions and expectations. And then, of course, very quickly happening on top of all this is the big data and artificial intelligence methods to collect huge amount of data that is spread in different databases around the world, and then extract patterns from those. So AI is allowing to make different questions because we can have different answers. We can have different ways of addressing all the questions and also ask new ones. So there's a lot of things going on, and the dialogue between these different approaches on top of what technology is favoring, then it's expected that new synthesis will be coming more and more often, helping us to understand what to expect. But then I will go bit a bit more focus on the experiments, because I particularly like a lot to conduct experiments, and because they have the as I mentioned before, they have the advantage of allowing us to test mechanisms of action. But then when you see the reviews on the approaches to analyze climate change or climate or global changes more in general, we see that most studies are actually focusing on very low levels of biological organization. So we see most of the studies here that was found in this review focus on physiological changes and at the individual level. Much less is done at community and ecosystem levels because it's complicated with experiments. And also many of these experiments to test the impacts of stressors focus on single species and not on a variety of species or even community as such. And this has puts limits to our understanding of real world responses. And there has been recommendations on how to address this by moving to more realistic experimental settings, such as those conducted in mesocosms. So get out of the lab and try to, or even in the lab, but try to move away from single species, single stressors, and very unrealistic, simplified settings to move towards mesocosms, which are considered the ideal size for experiments because they have kind of the best combination of realism, possibility to have replicates or gradient designs, and controls. So, but at the same time, mesocosms have a size that allow us to recreate at least parts of the ecosystems. And that's very more and more often done in freshwaters, where we can kind of mimic parts of a lake, for example, or parts of a stream, and then have interaction, have more species, and then have, as I said, this kind of best balance among these three major dimensions that need to be considered when we are in the empirical domain of research, when we move away from theoretical models and try to test what actually happens. So we have seen that global change stressors do affect ecosystems and their contributions. And we are seeing very briefly how some of these stressors can be addressed or best addressed, but there's the other side of the story. So ecosystems are not just passive, being impacted by global change. So ecosystems have capacity to respond. And we are seeing that different big stressors like agriculture, they decreases that capacity, that natural capacity to resist and to be resilient. That is to avoid shifting from the natural state. For example, here in this image represented by this little ball here, that would be the desired state of, let's say, a lake. And we see that agriculture, through these processes that are mentioned under the arrow, so above all, eutrophication, the loss of buffer zones, reduced water table, the frequent hypoxia, loss of big fish, which is one of the major consequences in fresh waters surrounded by agriculture, and the general loss of biodiversity. So all these mechanisms are eroded and facilitate this shift from this ecosystem here, pop, flipping, and moving to an undesired state. So agriculture is said to decrease the resilience of aquatic ecosystems, and once that ecosystem has received a lot of nutrients through agriculture or through any other intensive human activity, then there's a series of processes internal to the lake or to the river or to the coastal area, to changes in the chemical setting and in the major biological components such as fish and zooplankton and macrophytes, not shown in this graph, but they are also changed. And then through these internal interactions among them, they produce different feedback mechanisms that sustain and reinforce these eutrophic symptoms. But not just the symptoms, some of these changes, such as the increase in organic matter and therefore increase in oxygen consumption, leading to oxygen depletion, eventually favors the release of phosphorus that is stored in the sediments, which is called the internal phosphorus loading. And that is a self-reinforcing eutrophication. And that is seen even when the external load is controlled. So this is a kind of change that it's called a tipping point, because it's a self-enforced deterioration. So once an ecosystem has passed a certain threshold, then these internal mechanisms make it faster and faster in this wheel of, in this case, deterioration, leading or started with the external load of nutrients. So some ecosystems can have this kind of shifts, regime shifts, not all. There's a certain percentage that is seen that can make such changes, but they're not negligible. So there's a lot of research now trying to identify what are the conditions that make some of the ecosystems react in this fast and self-reinforcing way, and which mechanisms prevent that from happening, or at least make it more difficult to happen. And then we know that also climate warming decreases resilience. As here in the left, we see the changes promoted by the increase in nutrients, in eutrophication, and on the horizontal line here we see increases in temperature. And a lot of empirical evidence is indicating that under warmer conditions, then ecosystems have a lower capacity to cope with other changes, such as eutrophication. So climate change and eutrophication interact. Climate change enhances and favors eutrophication symptoms and eutrophication itself. And therefore, we see this interplay of these two major grand ecological challenges, climate change and changes in nutrient fluxes leading to eutrophication, interacting and making what is called a bad resilience mechanism. Why bad? bad from our point of view, because the state that is where fresh waters are eutrophic and warmer is very stable and very resilient, meaning that it will be difficult to get it back, right? There are some local aspects that make this not be universal. So that's interesting also to see how and when this interaction between these two major forces actually happened, leading to a more frequent dominance of cyanobacteria in eutrophic warmer systems. But then, what is resilience in the end? What do we mean with that? So resilience is a very general term, very often used in all sorts of situations and contexts. And with resilience, we're talking about the capacity to absorb the change without losing functioning. And in many fields, we see that resilience is considered a part of sustainability. So there's a lot of literature that says sustainable development or sustainable use of our natural resources make the ecosystems be more capable of preserving, of continue working in the long term, meaning they are more resilient, and a more resilient ecosystem has the capacity over time to face disturbance and keep sustaining life. So there is this feedback between sustainability and resilience, right? But in ecology, we can see, and this is very interesting, that there are like two major schools that very often don't talk to each other. And one is kind of the classic viewpoint of stability of ecosystems, which is very related to biodiversity. And then the other, let's call it school, which focus not on stability, but on resilience, as using that term. And that is very more linked to regime shifts, socio-ecological systems, vulnerability, sustainability, as I was mentioned before. So these two viewpoints very often are assuming they're using the same terminology often, and they are assuming different things. So it's a bit difficult sometimes when we want to measure resilience and measure stability. So not just talk about general mechanisms, but actually be able to quantify resilience and or stability. And these two schools also often are based on different theoretical works. So what I'm pleading now is that we have to really understand what's happening with our ecosystems, with these global changes. We need to be open and enrich our viewpoint from the different theories that are out there, and try to make our research to talk with these different schools of thoughts. And these different schools of thought and different theoretical frameworks tell us, when we combine, that the good resilience mechanisms are related to diversity. That would be the stability theoretical framework, diversity at the local and at the landscape level, but then also the other theoretical framework more related to resilience and these probability landscapes and the walls in the valleys, as I was showing. They also talk about internal mechanisms that are not related to biodiversity necessarily, but that are physical and chemical mechanisms, and that are key species or groups that have the capacity to provide resilience to the system. So these would be keystone species like fishes, piscivorous fish, for example, in lakes, and foundation species such as submerged macrophytes. So the presence of these key ecological groups makes the ecosystem be more resilient, good or bad, depending on the situation of that particular water body in a given moment. And then, besides the local processes, we need to consider what's happening in the landscape, because that water body interacts with also other water bodies and the terrestrial ecosystems where they are placed. So connectivity and dispersal are also crucial for this, for the action of these resilient mechanisms. And then the lack of this are, of course, by opposition, bad resilient mechanisms when these are lost. So in this super nice paper that tried to actually see and put some rationale behind these different theoretical frameworks that are up there, they made this list of terms and how to quantify what do we mean when we talk about these different components of resilience, such as resistance, such as recovery, latitude, temporal invariability, tolerance to changes, and so on. So for those that are interested in going deeper, I really recommend reading this very nice paper by Van Meerbeek and colleagues in Journal of Ecology a few years back. So back to how to study resilience. So many experimental studies are trying to see how ecosystems or this little part of ecosystems and communities respond to a particular stressor, a pulse disturbance or a press disturbance that tries to mimic one of the effects of a grand ecological challenge. But very few studies, when you see the literature, actually focus on the recovery. So what happens with that community or that ecosystem when the disturbance is lifted? And that's important because that allows us to see what are the mechanisms that can provide that capacity to recover. So there are some experiments where we have tried to see that and combine these multiple stressors, such as increase in temperature, mimicking warming, starting with natural communities, same natural communities exposed to different temperature treatments, and those ending communities being subject to another dimension of climate change, which is a sudden precipitation event. And then we tested the recovery capacity of the assemblage of species and how the different communities respond and recover from under these different warming scenarios, how they recover from this precipitation event. And we are seeing that cyanobacteria is both favored by warming and becomes dominant. This would be the treatment here, the red one, which is the higher temperature one, becomes dominated by cyanobacteria from a community that have over 30 original species at the beginning. And then this community is also extremely resilient to an extreme rainfall event. So the combination of different stressors is relevant to understand what can we expect with one of the major threats to freshwaters, that is the dominance of toxic cyanobacteria. But then also we can do that in artificial streams, where we can mimic sectors or sections of streams and have a more or less natural communities in these experiment, we tested the effect of, again, a simulated rainfall event, so increasing the flow, have a flow pulse into these different artificial streams that were also subject to other changes, such as different nutrient levels, and some were shaded and some have light. And then we were testing the combination of factors and how the communities have the capacity to react and to respond. And we see that this intense precipitation affects periphyton, affects the richness, and affects the biomass and promotes a loss. But some communities have a better chance to cope. So those communities that have higher nutrient concentrations and have better light conditions, they responded faster, recovered faster, therefore they were more resilient to this disturbance. But we're also seeing what happens in nature, not just in experiments. And then having been able to study or to follow same ecosystems along a series of years gives the opportunity to test what happens with climate variability and things that happen without being expected, like this massive drought that occurred in Uruguay 3 years ago. It was a combination of La Niña with unprecedented heat waves promoted by climate change, where the water for 2 million people was jeopardized for months. So people were drinking brackish water because this is the main reservoir in Uruguay. You see, it was absolutely dried, and the losses, economic losses, were massive. But we also lost a lot of small water bodies, like these artificial farm ponds here in the pictures in the middle and in the right, which we were studying, which we happen to be studied. And then we have this drought as a natural experiment. And we are analyzing the response and the recovery of communities and ecosystem functioning in a series of farm ponds that are like in the photo above with the green frame. These are ponds that have low cattle in their vicinities. So they're all cattle ponds, and those at the bottom with more intense livestock production, so with higher density. And we're seeing the reaction of these two types of ponds. We're studying many of them with with contrasting production levels in their micro watersheds. And we're seeing that the magnitude of drought is different at the ecosystem level. So these are processes at the ecosystem level above, and these are community process in the below part of the graph. And these are the low land use intensity, so few cows, let's say, and the high land use intensity, higher density of cows using those ponds. And we see the drought, the magnitude of the effects of drought depended on the context of land use intensity, meaning that the ponds that have a lower land use intensity are recovering faster. They're still not recovering, but because the resilience mechanisms were weakened, like macrophytes were affected and piscivorous fish were lost in all of them. But we're seeing that those that can recover faster are those that were subject to a lower pressure in terms of land use. So just to arrive to the final point of this talk is how can we move from describing these very often tragic impacts of these grand environmental challenges to enhance good resilience of ecosystems. So one way is that we need to improve our understanding of changes in key communities. We know that not all communities are have the same ecological value. So we're seeing that some have the capacity to transform the ecosystem state or to increase the ecosystem capacity to absorb changes without losing functioning. And we need to understand them more. And for that, combining approaches, as I mentioned before, is really what will make us truly understand and move faster and advance our knowledge on what are the mechanisms that we need to promote if we can, or to protect. And another kind of mind setting is that we need to do more research in solutions and not just describing impacts. So this image here shows for still freshwater, so for lakes and ponds. So the amount of researchers that are doing experiments to address the impacts of all this list of dimensions. So from climate change to nutrient pollution, so toxic chemicals, land use change, harmful algae, atmospheric deposition, all sorts of sources of negative impacts on freshwater. But look how little research is done to test the effects of actual solutions, like biomanipulation, bioremediation, catchment restoration, ecosystem engineering, and so on. So we are knowing a lot. Still, we need to understand more, but we're knowing a lot on the impact of the different dimensions of climate change and global change. But when it comes to solutions, we are very, very behind. So we're very often say, yes, we need to protect the ecosystem, but how? How much? Doing what exactly? And that's very often takes us researchers a surprise if a manager happens to ask us what to do, or when there is a change in law, like in Europe now with the restoration law. Then now people are trying to advance very fast to understand what needs to be restored and how much and which species. Is it habitat creation or resurrection? It's all worthwhile. We need to protect biological corridors. Yes. How? Which corridors? How do we protect them? How do we create them? So there's a lot of potential ways of enhancing the natural capacity of ecosystems to cope with change, and we need to know them. So for that, we need to use inter and transdisciplinary tools, talk with people, be creative, make networks, and try and address what makes ecosystems stronger. So with this, I would like to thank you all again for your attention and for your patience with all the technical problems. And I'm open for conversation. Thank you.
Thank you very much, Mariana. That was very interesting. Really great to keep in mind in the context of GLION as well, thinking about those solution-oriented approaches. So now we're going to open it up for questions from the audience. I'm going to stop the recording just because we usually don't include the Q&A portion in the YouTube video. So I'm going to stop that now. And then anyone